Good morning, learners. My name is Mr. Pochilola. Once again, we meet now to continue looking at measurements too. In lesson 1 of the topic, we looked at the two types of quantities with examples, namely fundamental or basic quantities and the derived quantities. So we looked at the definitions of these two important types of measurements with corresponding examples. We meet now to discuss three aspects of measurements, namely standard form and scientific notations of numbers. We shall discuss significant figures as well as prefixes of SI units. These are very, very important aspects of measurements in physics. If you're watching this video lesson on our YouTube channel, consider subscribing to the channel so that every time we upload a new material, you are notified on time. Welcome to Black Slides. Remember to invite your friends, your family members who are studying MSCE to join us, because this lesson is one of the important lessons in physics measurements too. So we are going to dwell on standard form and scientific notations of numbers. We are going to look at significant figures, what they are and why they are important. We shall also discuss prefixes of units. We shall look at what these are and why they are important in physics. Welcome, learners. Without further ado, let's look at standard notation and scientific notations. I'm confident that this is not the first time you've met this concept, which is called standard notation and scientific notation. It can be in mathematics, in physics, in lower classes especially. Can be in other subjects, but mainly mathematics and physics, as well as chemistry maybe. Standard notation and scientific notation. What do we mean when we say a number is written in standard notation or scientific notation? Really, what do we mean? Numbers expressed in powers of 10 are written in standard form. When you write a number as the power of 10, it is said to be written or to have been written in standard form. Standard form is also called scientific notation. So use standard forms and scientific notation to mean the same thing. Don't be confused. The usual way of writing numbers without powers is not standard form, it's what is called ordinary form. So when you write a number such as 589, That's an ordinary way of writing numbers. It's not standard. But when you express the same number as power of 10, then the number is to be written in its standard form, also called scientific notation. So scientific notation or standard form, standard notation is the same thing basically. For example, a number such as or a quantity such as megawatt, 1 megawatt, 1 megawatt of electrical power is 1000 watts. 1 mega means 1000. So this number here is not in standard form, it's not in scientific notation. It becomes scientific notation or standard notation when it's written as the power of 10. So 1 million watts can be written as 1 times 10 to the power 6. So this is called standard notation, also called scientific notation. Welcome learners. So 1 million is the same as 1 times 10 to the power 6. So 1 million watts is just as good as 1 times 10 to the power 6 watts. So this number is said to be in its scientific notation or standard notation. Welcome learners. So 1 times 10 to the power 6 is the scientific notation or scientific way of expressing the number 1 megawatt. Mega means 1000. So standard form makes very large and very small numbers easier to write and read. So scientists, physicists, including you physics students, agreed to write numbers that are very large or the numbers that are very small using standard form because it makes the numbers, the very large numbers and very small numbers easier to write and read. Welcome learners. So the expression 1 times 10 to the power 6 means 1 multiplied by 10 raised to the power 6. So this power of 6 here indicates the number of times 10 is to be multiplied by itself to give us back 1 million. Which I mentioned that 1 million as written like this is the ordinary way of writing numbers. But when you express it as 1 times 10 to the power 6 watts, it becomes scientific notation, also called the standard notation. Welcome learners. Some examples of standard notation, also called scientific notation in physics. Numbers such as 1 billion is written as 1 times 10 to the power 12. Check that this number has 12 zeros. So 1 times 10 to the power 12 is the scientific notation, also called standard notation. It's read as 1 times 10 to the power 12. So easy to read this same number when expressed in a scientific notation or standard notation. So all you have to do is shift the decimal. There's purportedly a decimal number in front there, a decimal point. So you simply count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Making sure that the first number, this one here, lies between 1 and 10. So this number is between 1 and 10. 1, because inclusive. Alright, so 1 times 10 to the power 12 is the standard notation of this big number here. So it's more appropriate in physics to write this big number as 1 times 10 to the power 12. The number that has 9 zeros, 1 times 10 to the power 10 to the power 9. This number here is in standard notation is going to be 1 times 10 to the power 9. So this is the standard notation of this number here. So instead of writing a number with a lot of zeros like this, just write 1 times 10 to the power 9. So this is the standard form. And the first number here is a number that lies between 1 and 10, including 1 itself. And it should be between 1 times 9.99999, or essentially between 1 and 10. Alright, so take note. So we have 1 times 10 to the power 9 is the same as this number. So it's more advised that your number should be written as 1 times 10 to the power 9. Welcome, learners. So that 1 million shall be 1 times 10 to the power 10, 1 times 10 to the power 6. So this is the standard notation of writing the number 1 million. Welcome, learners. Sometimes you have numbers that are below 0, like 1 over 10. 1 over 10 is the same as 0.1. So in order to write 0.1 in standard notation like this, simply shift the decimal so that the number that comes first is between 1 and 10. So in standard notation, 1 over 10 is 1 times 10 to the power minus 1. Take note of that. So first write 1 over 10 as 0.1. In standard notation, simply shift the decimal so that it starts with 1. So when you shift a decimal to the right, it becomes 1 times 10 to the power minus 1. So this is the standard notation of the number 1 over 10. 1 over 100, which is the same as 0.01, is 1 times 10 to the power minus 2. In standard notation, 0.01 is the same as 1 over 100. Written in standard notation, it's going to be 1 times 10 to the power minus 2. One over 1000 is as good as 1 times 10 to the power minus 3 in standard notation. In case you have questions, don't hesitate to reach out to me on the number that is shared earlier, or you can simply leave a comment in the comment section below. Welcome to Prefixes of SI units. What are prefixes? What do you think prefixes are? What are prefixes? Some numbers that you are going to encounter in your measurements can either be very large or very small. Some numbers can be very large or very small. So these numbers are represented using prefixes in order to make them shorter and easier to write. So in other words, prefixes are simply a way of writing numbers that are either too large, or very small, so that they're shorter and easier to read and write. So prefixes make numbers shorter and easier to write. So we define a prefix as simply an extra symbol added to an SI unit to indicate a multiple or a fraction of the unit. So a prefix is a symbol. It's not a number on its own, it's just a symbol which is added to an SI unit to indicate a multiple or a fraction of the unit. We're going to look at some examples of this. So some common examples of prefixes of SI units. These you must commit to memory. You must know them off by heart. You will not be given a table indicating what each is, what each means in an exam. So you need to know these off by heart. So we have a prefix, a symbol, its meaning, as well as some examples. A terra. represented by symbol T, capital T, means 1 multiplied by 10 to the power 12, with 1 and 12 zeros in front. That's a tera. For example, I'm sure you have heard about terabyte. Terabyte is a very big unit of data or device storage. Terabytes. In short, it's written as TB. So when you have a terabyte of your computer hard drive, it means it has this big number of bytes. Another one is a giga. Giga is presented as G, which is 1 billion or 1 times 10 to the power 9. So gigabyte, in short GB, means this amount of storage or data. While a mega, each time we hear mega, it means it's a million of something. So 1 times 10 to the power 6, as in a megawatts of electricity, means 1 million watts, written in short as MW. Kilo means 1000. Like kilometer, it means 1000 meters. So instead of writing 1000 meters, you simply write km to mean kilometer. Kilometer. Anyone who knows what a kilo is will know that you are talking about 1000 meters. So the first 5 we've discussed are considered to be big prefixes, or prefixes used to stand for big numbers starting from 1000 going up, start from kilo, mega, giga to tera. That's in ascending order. Starting from this going down, the values keep decreasing. So this from this to nano, this is descending order. From kilo going upwards, that's ascending order. Big values. So this short d means 1 over 10 or 10 to the power minus 1. For example, decimeter. Decimeter means 1 times 10 to the power minus 1. Cent, C, represents 1 over 100, which is same as centimeter. Cm means centimeter. Centimeter is 1 times 10 to the power minus 2. Mil, as in millimeter, it means 10 to the power minus 3 or 1 over 1000. So this commit to memory so that you know when and how to use them in your measurements or in your calculation. A micro, represented by the symbol mu, the Greek letter mu, is as good as 1 over 1000, which is the same as 1 times 10 to the power minus 6 microseconds. And then lastly, we have a nano. Of course, there are others like the picos, the femto, and others, but I just picked these most common ones. So a nano n, small n, is 1 over 1 billion. That's 1 times 10 to the power minus 9. That's called nanoseconds. In our next lesson, we are going to look at how you can convert from one prefix to another. That's going to be a separate lesson altogether. Welcome, learners. Lastly, in this lesson, let's discuss significant figures. You have seen questions that say leave your answer to two significant figures, or to one significant figure, or to three significant figures. What does that mean? What does that mean? So we are going to discuss this now. So by the end of the lesson, you should be able to express a number, any numbers, to a required number of significant figures. Definition of significant figures. We define significant figures as digits in a measurement that are known with certainty, plus the first uncertain or estimated digits. So in other words, the significant figures are just digits that you are sure to represent the quantity, and in addition to another digit which you believe to be uncertain, or you believe that it is just some kind of rounded off digit. So the digits in a measurement that are known with certainty or surety, plus the first uncertain or estimated digit that makes it these significant figures. In fact, the word significant in everyday usage means important. But here we are not using the word significant figures to mean the term significant figures to mean important figures, no. But why are significant figures important anyway? Why are significant figures significant? Right. Significant figures show the precision of a measurement. Remember that precision is a repeatability of values in a measurement. How close measured values are to each other in a measurement. Alright, that's called precision. It's not the same as accuracy. So significant figures show the precision of a measurement. Alright. Significant figures when used, prevent giving results that appear more accurate than the measuring instrument allows. So it prevents giving results that appear more accurate than the measuring instrument allows. So they represent precision rather than accuracy. We also use significant figures when recording and calculating measured values, as we shall see in some examples. So suppose you're measuring the length of a wire, and you are told to leave your answer or your measurement to two significant figures. That's important because the two significant figures demanded will represent how precise your instrument is, or to what degree your instrument is precise. So let's look at some important rules for counting significant figures. In a measurement, when you get a measurement of some quantity in physics, all non-zero digits in that measurement are significant. They're significant. For example, numbers such as 25, both 2 and 5 are non-zeros. So 25 has two significant figures, 2 and 5 are both significant. That's applying this first rule here. All non-zero digits are significant. The numbers such as 478, 478, they are all non-zeros. There's no zero here. So this is three significant figures. Numbers such as 9265 has four significant figures. 1, 2, 3, 4. Welcome, learners. Rule number 2. Zeros between non-zero digits are significant. So when you have a zero between non-zero digits, that zero is considered to be significant. So numbers such as 1002 has four significant figures. So the zeros in between 1 and 2 are included. So 1002 has four significant figures and not 2. Numbers such as 3.005 has two zeros between 3 and 5. Therefore, the number has four significant figures. Numbers such as 7008 has four significant figures. The zeros between 7 and 8 are included. They're considered to be significant. Welcome, learners. So Zeros between and 0 digits are significant. Leading zeros are not significant, meaning that zeros that lie between or that come at the beginning, like 0.0045. So the first three zeros are not significant. Therefore, this number has two significant figures, 4 and 5. A number such as 0.00086 has two significant figures. So the first four zeros are insignificant, are not significant. 0.05670 has four significant figures, 5670. Rule number 4. Trailing zeros to the right of a decimal point are significant. So when zeros come after a decimal point, those zeros are significant. For example, 2.30 has three significant figures, but 2.3 alone has two significant figures. 2.30 has three significant figures, while 2.3 has two significant figures. Take note of that. So these are three significant figures. Zeros after decimal are significant. Numbers such as 5.700 has four significant figures and not two. But if you write the same number as 5.7, that has two significant figures. 5.700 has four significant figures because trailing zeros to the right of a decimal point are significant. 80.00 has four significant figures, but 80 alone without decimals and zeros after that has one significant figure. Rule number 5. Trailing zeros in whole numbers without a decimal point are usually not significant. Examples abound. 1500 has two significant figures and not four. So the zeros after the 5 are not significant. 47,000 has two significant figures rather than 5 significant figures. So to show these zeros are significant, use scientific notation. Alright, so in this case, the number 1500 is, in scientific notation, is 1.500 times 10 to the power 3. So we have made these zeros significant. A number that was initially that had two significant figures, 1 and 5, now has four significant figures. The moment you write the number in standard scientific notation, the number of significant figures changes. And therefore, 47,000 written in scientific notation is 4.70000. We have made the zeros significant, so the whole number, now this whole number has 1, 2, 3, 4, 5 significant figures. There are times when you must round off numbers to show which numbers are significant. There are times when you try to round off numbers to show which ones are significant in your measurement. Let's suppose that you're asked to round off a number to one significant figure. For example, a number such as 36. The one significant figure is going to be taken as 40. So in order to do that, you simply consider the number that precedes or that comes after 3 is 6. If this number is greater than 5 or 5 and greater, you'd consider that as a 1. So you take that 1 and add it to the 3. So when you add the 1 to the 3, you have 4. So it will be 4, 0, 36. As rounded off to one significant figure is 40 or 40. So what's happening here? There's 3 is taken, the 6 is considered to be a 1. So you take a 1, add to the 3 to give you a 40. Since the number after the decimal is not yet 5 and above, so this is considered to be 0. If the number is less than 5, this is considered to be a 0, so the 0 added to 8 gives you 8. So 8.4 is 8 to one significant figure. That is 6 is the same as 40 to one significant figure. 0.076 to one significant figure. The number to consider here is the 7. But in front of it there is a 6, which is 5 and greater. This is 6. So you take the 6 as a 1, and then you add that to the preceding number, the number before, it will be 8. So 0.076 is as good as 0.86. Excuse me. 0.876 is the same as 0.08 to one significant figure. Welcome, learners. Two significant figures. When a number needs to be expressed to two significant figures, numbers such as this, you consider the first two digits as it is 4 significant figures. So you consider the number after the decimal is 7. It's greater than 5. So you take that to be a 1. So 1 added to 36 becomes 37. which is to two significant figures. To two significant figures, 0.076. The numbers to be considered for two significant figures is 76. So 76 rounded off to two significant figures. You consider this number which is less than 5. Therefore, the number to two significant figures is going to be 0.076. (458) to two significant figures. The numbers under consideration are 4 and 45. So we consider the third number, which in this case is already greater than 5. So you take that as a 1. Add to 5 to give us 46 or 460. So this number is to two significant figures. Then to three significant figures, numbers such as 5.6789, the numbers to be considered are going to be 5.67. This is the first three significant figures. So the number that comes after the 7 is already greater than 5, so we take that as a 1 and add it to the 7. It will give us 5.68 significant figures. So there are three of them. I hope you have found this lesson useful, and let me encourage you to master these rules and apply them in your measurements. So 0.004567 to three significant figures. You consider the first three numbers, 1, 2, 3, round this off, so you consider the number that comes at the end is 7. 7 is greater than 5, so you add that as a 1 to 6, it will be 0.00457 as a number containing three significant figures. Welcome, learners. Lastly, numbers such as 7,896 can be written to three significant figures. Unfortunately, here we need to be careful. 789, the number that comes at the end is a 6. If you take this as a 1, you add to 9, it will be 10. That will affect the result. So the number is going to be 79800. 7900. So if you take this as a 1, you add to this, it's going to be 10. The 1 from 10 added to 8 to be like 79. But this number isn't to three significant figures, it's basically 2. Remember that zeros, trailing zeros at the end of the non-zero number, the zeros are insignificant. So here the number, this number here has two significant figures and not three. Welcome, learners. Expecting to meet you with more examples when we meet again in our next lesson. My name is